Okay, today we're going to be talking about the number e, and I know e sounds like a letter, but it's a letter that we assign a given number. Just like we assign pi the number 3.14, I guess we assign 3.14 the letter pi, there's a number that is assigned to the letter e. Now what we're going to do is we're going to look at y equals 1 plus 1 over n raised to the n power. And I'm going to go ahead and plug that into y equals in our calculator here. 1 plus 1 over, we don't have an n, but we do have an x, raised to the x power. And what I want to do is I want to look at values for y when n is 10, 100, 1,000, 10,000, and 100,000. So I'm going to look at my table here, but I'm going to do a couple things with my table. I'm going to change my independent variable to ask. So we're going to go to table. And so now I want to know what is y when x is 10. So I'll plug in 10. And we're getting 2.5937. Now I want to know what is y when x is 100. And we're getting y is 2.7048. When x is 1,000, that's y is 2.7169. Now we'll do 10,000. Oops, one too many zeros. And that's y is equal to 2.7181. And now let's do 100,000. And we're getting y is 2.718. And now this says a 3 right here, but that's because it's rounding. There's no more places to put more decimals here. And so what happens is that as x, or n in this case, is getting larger and larger, okay, this value here is getting closer and closer to 2.718. And this is what we call the number e. E is approximately, and there's a button for it on your calculator here, second, and then we have e raised to the first power. E is 2.718, okay, 281828, and it goes on for forever and a day. This is an irrational number. There's no pattern to the numbers after the decimal point. Okay, you can't represent it as a ratio of two integers. And again, this is called the number e. Now the history of mathematics is marked, and you don't have to write this part down, but the history of mathematics, marked by the discovery of special numbers such as counting numbers, which would be like 1, 2, 3. 0 was a big discovery, negative numbers, pi, which we already kind of talked about, and imaginary numbers, which we learned about in the first semester. In this lesson, we're going to study one of the most famous numbers of modern times, and like pi and the letter I, the number e is denoted by a letter, and the number is called the natural base e, okay, or Euler number. And they called it Euler's number because Leonard Euler was the person who discovered it. Again, but what you really need to know, just like you know that pi is 3.14, you really need to know that e is 2.718. Alright. Now, we're going to graph each of the following and state the domain and range. We're going to label any horizontal asymptotes we have. So we have y is equal to e to the x power. This is an exponential function. Remember, e is just a number. So this is an exponential growth function. Exponential growth. And we know basically what an exponential growth function is going to look like. Okay, it's going to start out here and then it's going to skyrocket. And so what we want to do is we just want to make a table of values when x is -1, 0, 1, and 2. And so into y equals, we're just going to put e, and the e is located right here above the button that says ln, and we're going to be learning about that later. But e to the x, close my parenthesis. I need to go back to my table and turn the independent variable back to auto. and then look at my ordered pairs here. So when x is -1, y is about 0.36, and that gets rounded to 8-ish. Okay? When x is 0, y is 1, and we know that because e to the 0, remember this is just a number, and any number raised to the 0 power is 1. E to the first power, 2.718-ish, and e squared is 7.389-ish. Now we just want to plot these. -1.368, that's kind of right there. 0, 1, right about there. 1, 2.718-ish, here's 1, 2, and so we're kind of right about there. And then 2, 7.389-ish. 1, 2, 3, 4, 5, 6, 7, and then a little less than halfway up to 8. Now, just like all our other exponential functions, there is a horizontal asymptote here. We're going to label that y equals 0, because these numbers are going to get smaller and smaller and smaller, but they're never ever going to go below the x-axis. And that's what e to the x looks like. Now remember, y equals e to the negative x. We want to rewrite this as 1 over e to the x power. 1 over e is 1 divided by 2.718. We know that that is less than 1, so this right here is exponential decay. And we also know what that graph looks like. And so we're going to make another table of values. Y equals 1 over e. There is just an e to it right here. I pushed the second and the divide by, and that gave me an e. Raised to the x power, that is e to the negative first, or the negative x power. We're going to look at our table of values, and we see that when x is -2, we're at the 7.389. -1 is the 2.718. 0 is still 1, and 1 is 0.3678. And you'll notice that as x gets larger, these numbers get smaller, but they're never going to get negative. So there's another horizontal asymptote right here at y equals 0. Plotting our points, -2, 7.3, that's going to be right about there. -1, 2.718, right about here. 0, 1, right there. And then 1, 0.3678. And so we're coming down. We're approaching 0, but we're never actually quite getting to 0. We're just getting smaller and smaller, so we're hugging that asymptote as we go out. Just like every other exponential growth and decay function, domain for both of these is all real numbers. The range, just like all other exponential decay functions and growth functions, y is greater than 0. And then there is an asymptote here at y equals 0. Okay, so we're going to describe the transformations of each of the following graphs from y equals e to the x. We're not going to sketch the graphs, okay, because we got some other things we need to do. Looking at here, I see a 2 on the outside, and so that is a vertical stretch. By a factor of 2. Again, that was because of this 2 right here. Let me get some other colors. Because of the -1 right here, subtracting 1 on the inside, that is a translate or a shift right 1 unit. And then because of the +5 on the outside, that is translate to up 5 units. Okay, so vertical stretch by a factor of 2, translate right 1 unit, up 5 units. For here, y equals negative e to the x plus 2. Because of the minus on the outside there, that is a reflect over the x-axis. And then with the plus 2 on the outside, translate up 2 units. Okay, so our rules that we've been doing with our exponential growth, with our square root function, with our cube root function, with any function really, they still apply to e to the x. Now we can also simplify expressions with the natural base e by using properties of exponents. All of these properties still apply. So e to the third times e to the fifth, ask yourself, what are we doing with those exponents? We're going to add those, e to the 3 plus 5, and so we get e to the 8th power. For number 2, we have 2e raised to the 5th. My eyes are drawn to this parentheses. Everything on the inside wants that power of 5. So 2 gets a power of 5, and e gets a power of 5. And then we know who 2 to the 5th is. That's really easy. 2 to the 5th is 32, and then you have e to the 5th power. Now over here, 27e to the 4th over 3e to the 9th. First I see 27 over 3. Okay, I know both those numbers are divisible by 3. That's just a fraction. So we're going to divide by 3. We're going to divide by 3. 27 divided by 3 is 9. 3 divided by 3 is 1. And then you see e to the 4th over e to the 9th. Ask yourself, what do you do with those exponents? We're going to subtract. There's more e's in the denominator, so it's going to be e to the 9 minus 4, e to the 5th. You don't have to write the 1 there if you don't want to. 9 over e to the 5th power. Over here, my eyes are immediately drawn to this negative exponent. Remember, negative exponents, what they want to do, they want to move. So this is going to move to the top. That becomes 2e to the 3rd, e to the positive 4th now. And then think about what you're doing with your exponents. 2e to the 7th power. Down here we have the cube root of 64e to the 18th. Remember that whatever your exponents in here, they need to match your index. And so we're going to rewrite this as the cube root of 64 is really 4 raised to the 3rd power. And then e to the 18th, we need to change that to be e to the 6th raised to the 3rd power. And so then I know the cube root of 4 to the 3rd is 4. The cube root of e to the 6th to the 3rd is just e to the 6th. And that's that. Short notes today. We do have some applications, but we're going to be learning about them tomorrow, more with compound interest. See you then.